speak. I want to tell you a little bit about some progress we've made in the last few years in sort of the interface between geometric and algebraic topology. So that means the topology of manifolds, basically. We've got to the stage where we can say some things about incredibly basic objects in the topology of manifolds, namely Euclidean space. So what I want to tell you about today is what we know as of now about the symmetries of Euclidean space as the topological symmetries of Euclidean space. So the group of homeomorphisms of d-dimensional Euclidean space, so that's just a set of functions from Rd to Rd, which are continuous bijections and have continuous inverses. I want to consider this set, but I want to consider it as a space, of course. I know what I mean to say that two functions are near to each other, of course. It means they're point-wise quite near to each other. And so I give this space a topology. There's only one way to do that, basically, which is the topology of uniform convergence on compact sets. So this is the space I'm interested in. And I'll phrase most of the results that I'm talking about today in terms of this space, but there's a few auxiliary spaces that will show up, and let me introduce those as well. So there's another kind of symmetry of Euclidean space you could talk about. You could look at the smooth symmetries of Euclidean space. And I'm saying here compactly supported smooth symmetries, so compactly supported diffeomorphisms of Euclidean space, meaning those which outside of some big compact set are just the identity. Okay? So these two characters will show up quite a lot. But when I describe these two, then there's also two obvious other characters I haven't mentioned, right? I could say homeomorphisms which are compactly supported, and I could say diffeomorphisms which are not compactly supported. And those, it turns out, are both much easier, and we know everything about them. So these are the two cousins of the two things I'm talking about. If we take compactly supported homeomorphisms of Euclidean space, that's a contractible space. If I have any compactly supported homeomorphism, say its support is this ball here, I can conjugate it by a rescaling. And then its support becomes this ball here. And I can carry on conjugating it by rescaling, so its support becomes very small. And C0, that converges to the identity. And if we're doing homeomorphisms, then C0 is the only game in town, and so that converges to the identity. So by scaling inwards, any compactly supported family of homeomorphisms is canonically, basically, by this mechanism, the same as the identity. So that's nothing. And the other thing we can do is we can look at all diffeomorphisms of Euclidean space without constraints on their support, so all diffeomorphisms. But there we can do the opposite trick. There we can scale outwards. If I take a diffeomorphism and scale outwards by more and more and more, it converges to its derivative at the origin by the definition of the derivative. And so that gives me a canonical way to start with any diffeomorphism and canonically isotope it to one that's a linear diffeomorphism, i.e. just a d by d matrix invertible. And then, of course, you can do the Gram-Schmidt process to canonically make that into an orthogonal linear isomorphism if you want. So this is just homotopy equivalent to the orthogonal group. So these are the two cousins of the two spaces I'm talking about. They're, of course, interesting, but we already know everything about them. And these four spaces, it turns out, are related to each other in a kind of incredible way. This is a sort of equation between these three spaces, or four spaces, sorry. It says if I look at the difference between the compactly supported homeomorphisms and the compactly supported diffeomorphisms of Euclidean space, then up to some algebraic topological noise, which is taking the d-fold loop space of the things involved, it's the same as the all homeomorphisms modulo all diffeomorphisms. And this is an incredible theorem of Morley. It's true in every dimension apart from 4. And if I use the notation I've introduced above to rejig it a little bit, what it says is that the space of all compactly supported diffeomorphisms is the d plus 1-fold loop space of top D mod OD. And given that I've told you OD is a compact Lie group, we know everything there is to know about the topology of OD. So this basically says that knowing about top D, the group of homeomorphisms, is the same information as knowing about the compactly supported diffeomorphisms, in some sense. But some are more convenient from some point of view than others, but this is somehow saying that really we're studying the same thing. So if you're more of a differential geometry-minded person, then you can imagine all my results are really about diffeomorphisms, compactly supported. But I'll phrase them all in terms of homeomorphisms because that has a bit better structure. So here's another point of view on this. There's a canonical decomposition of the group of diffeomorphisms of the D-sphere into the isometric diffeomorphisms, so the group OD plus 1, which is the sort of diffeomorphisms that we think about when we think about manipulating a sphere. The group of diffeomorphisms of the sphere is not OD plus 1. It's OD plus 1 times the compactly supported diffeomorphisms of RD. This is not very difficult, but what this means is that these compactly supported diffeomorphisms of RD are also exactly the difference between all smooth symmetries of the sphere and the ones that we sort of are able to think about, basically, like the linear isometries or things like that. And that means that, of course, studying this is just outside of our intuition, because in all the dimensions that we can think about, 1, 2, and 3, there is no difference. I mean, for dimension 1, you can do it yourself. You can prove that every compactly supported diffeomorphism of the real line is canonically isotopic to the identity, because it has to be monotone, and you just... in dimension 2, you can't do it yourself, but Smale did it using uniformization for Riemann surfaces, and in dimension 3, it's the theorem of Hatcher, which has recently been reproved by Bamler and Kleiner using weakly flow methods. But we now know that this is false in every dimension bigger than 3. It's the theorem of Watanabe, that for every dimension larger than 3, the group of compactly supported diffeomorphisms is not contractible. It's definitely not. In other words, the smooth symmetries of the sphere, there's strictly more of them than the ones that we know coming from linear algebra. And of course, it's good to know the space is not contractible, but I would like to know if it's not homotopy equivalent to a point, so what is it? Not what isn't it? So that's somehow what I'm interested in. What can we say about the topology of this space now that we know that it's not just contractible? So in the talk, I want to explain roughly the state of the art of what we know about this question as of now, and then I want to formulate a proposal for something like a complete description of the answer. We don't know this is true yet, but I'm very confident it will be true. And it sort of gives a complete answer in homotopy theoretic terms. So the way I want to state answers, as I said, I'll state everything in terms of homeomorphisms because it's a bit more convenient. And the way I want to communicate answers to you is by telling you what we know about the homotopy groups of these spaces. Okay? So for the experts, I'll phrase things in terms of homotopy groups of the classifying space of the group of homeomorphisms. But in fact, that for the non-experts, that makes no difference. That just corresponds to a change of indexing in homotopy groups. So you can forget what B means. I'll always write it, but you can always forget it. It's just a re-indexing. So what I'm thinking about is the homotopy group, so the spaces of maps from a sphere to the group of homeomorphisms up to homotopy. And then to make life easy and to make life practicable, in fact, I'll also rationalize those abelian groups. So that's how I want to communicate answers to you. And as a warm-up, let's first do all diffeomorphisms of Euclidean space, which is the same as the orthogonal group, as I just explained. So this is quite practical to calculate because the D plus first orthogonal group acts on the D sphere transitively, and the stabilizer is the Dth orthogonal group. And so we have this sort of equation that the space of cosets of OD and OD plus 1 is the D sphere. And so that sort of suggests an inductive scheme for proving things about OD, namely you do it by induction on D using the fact that the difference between two orthogonal groups is a sphere, and maybe we can think about the sphere. So this line of thinking gives a so-called long exact sequence of homotopy groups that relates the homotopy groups of OD, OD plus 1, and the D sphere. And of course, studying homotopy groups of spheres is not so easy. It's an entire industry in algebraic topology. But there's some things we do know. One very easy fact is that if you try to map a smaller dimensional sphere to a larger dimensional sphere, you can always contract it to a base point. So in other words, the homotopy groups vanish when I is less than D. And that means, if you just think about this sequence, that means that the homotopy groups of BOD, if you fix a degree, they stop changing as soon as D is big enough. It's called stabilizing. So that means actually there's not somehow some two-parameter family of things that you need to calculate. There's much less information than you might have thought. And a slightly more difficult but very classical theorem due to Serre is that we also know what the homotopy groups of spheres are if we rationalize them, if we tensor them with Q. I won't say what the answer is, but we know it completely. And using these sequences and using the calculation for the sphere, you can go away and on one side of paper, you can calculate what the homotopy groups of BOD are. And they have this form. So the things of this nature will show up a lot, so I'll spend a bit of time on it now. So when I write pi star of BOD, I'm thinking about the collection of all homotopy groups. So star is like a variable. And I'm thinking about it as like a graded vector space, so a list of vector spaces. And I'm saying it's the following graded vector space. It's a copy of the rational numbers every 4 degrees, so in degree 4, 8, 12, and so on, starting at 4 and ending at 4 times this number up here. And in addition to that, there's another copy of the rational numbers in degree d if d happens to be even. And otherwise, that's it. So this is a complete description of the homotopy groups of the rational homotopy groups of OD. So that's very attractive. These copies of Q also have a meaning. I mean, they're not just some random vector space. We don't know what it means. They correspond to characteristic classes that you might have studied in a course on algebraic topology. These ones in degree 4i are the so-called Pontryagin classes, and this one in degree d, when it exists, corresponds to the so-called Euler class. So this is all very symbolic. So this is what it actually looks like. So this is a chart of the homotopy groups of BOD for d even and d odd. And we sort of see that there's there's a pattern, clearly. Let me not try to be more precise than that, but when we look at this, we agree that there's a pattern, okay? And the pattern seems to have some kind of horizontal behavior, and then some kind of slope 1 behavior, or these blue dots, and then some kind of slope 2 behavior, which is somehow the absence of more orange dots. Okay? So it's somehow, there's some sort of, let's just call it a pattern. So I want to now tell you, so that was OD. I now want to tell you what we know about top D, so homeomorphisms of RD, by 3 short stories. So there's a classical way that you can try to study diffeomorphism groups of, in principle, any manifold. And it's a 3-step method. None of these steps are practical in many examples. But for the disk, it turns out that they're practical. And the method has an intrinsic limitation. It can only tell you, if you're studying symmetries of a d-dimensional manifold, it can only give you information up to about 1/3 times the dimension of the manifold. Okay? That's not because it doesn't work. That's not because no one's proved that it works in a better range or somehow. It just is not true that it gives you complete information. Okay? It has an intrinsic limitation called the Igusa stable range. But if you take this method and you apply it to diffeomorphisms of RD, compactly supported, and then you do the translation to top D, which I will do in my head and just write down the answer for you, you get the following formula. So it looks somewhat similar. So I'm again writing it as a graded vector space. It again has all these things in degrees 4i. I didn't write an upper index anymore, so it's all of them. And then it also has some stuff over here that's a bit more complicated than what happened for OD. There was still a class in degree D if D is even, just like there was before. But now there's classes in degrees d plus 5, d plus 9, d plus 13, and so on, when d is odd. And they weren't there before. So this is some new phenomenon that's fundamentally topological and is not visible smoothly. And just like before, these classes are not just symbols Q. I mean, they all have a meaning. The ones in degree 4i are still these Pontryagin classes. The ones in degree d is still the Euler class. And the other ones, it turns out, have something to do with algebraic K-theory of the integers. Whatever that is, that's something that you should be surprised that it has to do with homeomorphisms of Euclidean space. Okay? That's something essentially in number theory. And it turns out that all this stuff in this parentheses over here is exactly Borel's calculation of the rational K-theory of the integers. But because of this Igusa stable range, this formula is only correct in degrees up to about 4/3 times the dimension of, or 4/3 times d. Okay? It's d plus 1/3 times d. So in fact, the fact that I didn't put an upper index here like I did on the previous sum is irrelevant because I'm only making a claim in the range where the index doesn't matter anyway. But nonetheless, I'm going to write it that way. So this is somehow the classical story about what we know about homeomorphism groups. So this is in the 70s and 80s. More recently, Kontsevich proposed this way of understanding or of extracting cohomology classes for diffeomorphism groups with some extra decoration, framed diffeomorphism groups, using what are called configuration space integrals. So basically, you look at your family of Euclidean spaces, you look at configurations of some number of points in them, and then you integrate certain canonical differential forms over the configuration space, and you do some complicated combinatorics of how to glue all those spaces together. And those combinatorics are encapsulated in what's called these days a graph complex. So this somehow was done in detail by Watanabe in the sort of extreme degree that corresponds to the graphs being trivalent. And let me just show you what he said. He said the following. In any dimension, there's a surjection from certain homotopy groups. Don't worry yourself unduly about the index. Certain homotopy groups of top D onto a vector space of certain trivalent graphs. Okay? And there's an index R, which corresponds to the index R over here. And this vector space of trivalent graphs is the following. You look at the vector space of trivalent graphs, so graphs where every vertex has exactly 3 edges coming into it, that have R plus 1 many loops, or in other words, whose Euler characteristic is minus R. And then you say, if I have 3 graphs that only differ inside a little ball, and they differ exactly as these 3 pictures indicate, so-called IHX relation, then you say that linear combination of graphs is 0. Okay? And you also put in certain signs, which is why there's a plus version and a minus version of this complex. I won't tell you what the signs are. It's traditional to be very vague about that. So this is some vector space. He proves it subjects onto this vector space. And I mean, to finish the story and make it interesting, the vector space is also not 0. So one can compute by computer the dimensions of these vector spaces. There's 2 flavors depending on the sign. And sometimes they're 0, sure, but mostly they're non-trivial. So this shows, because Watanabe's map subjects onto this vector space, it shows that the domain has to be at least as big as the thing it's mapping onto. And here I've written ... but this is actually the limit of how many are computed. It turns out if you want to compute something that has a basis of all graphs that have 11 loops, there's quite a lot of such graphs, it turns out. So that's as far as you can go. And I phrased it here for dimension at least 5. I mean, Watanabe actually proved something in terms of diffeomorphism groups. And that statement is true in dimension 4 as well. I have to say dimension 5 because this theorem of Morley didn't work in dimension 4. And so this is actually what proves this fact, that diffeomorphism groups of any space of dimension bigger than 3 are not contractible. It's because they always have some homotopy group that maps onto some non-zero vector space. So this is the second of my short stories. So this says there's some other phenomenon going on. And the third one is a recent theorem of, or not so recent anymore, recent in my mind, theorem of Michael Weiss. Here I've just written down what I had before, so the answer for BOD and the answer in a range due to Farrell and Xiang for B top D. And this slide is very unsatisfying somehow. So firstly, I've phrased Weiss's theorem in a way that is unrecognizable if you look at this paper. But what it basically says, sort of just don't try to read it. What it says is that these Q to the 4 i's in B top D, even outside of the range where BOD has copies of Q, they're still there in B top D. Okay? So that says there's certain degrees I strictly bigger than D plus 1 over 2, and certain classes in B top D that correspond to the 4ith summand, even though that's not there in BOD. And the point of this is that the lowest one of these classes, if you think about it, it has degree approximately 4i, which is about 2 times D, which is way bigger than the Igusa stable range, which is 4/3 D. So this is saying something is happening way outside the range where we have a right to expect this equation to be true. But it's saying that this summand, at least, seems to still be there, even outside of the range where we know this equation is true. So this is, I agree, this is a bit difficult to explain. I mean, the actual statement he proves is a little more technical, and this was the best simplification I could make of his statement. But right, it's far outside the Igusa stable range. But in proving this theorem, Michael Weiss introduced an idea which, in fact, he points it out in a remark in the paper, saying, oh, it's like, this is quite interesting as well. And this idea has been very influential over the last few years and has led to more or less all the new progress we have about diffeomorphism groups of simple manifolds like disks or Euclidean space or things like that. So using this idea in Weiss's argument, Alexander Coopers and I decided that we would just try to calculate what the homotopy groups are in as big a range as possible using this new idea of Michael Weiss's. And this is one way to formulate what we showed. We showed that this formula of Farrell and Xiang is correct not just in a range of degrees, up to 4/3 times d, but it's correct outside certain bands of degrees, which I've written as a formula. Looking at the formula is not very enlightening. I'll show you a picture on the next slide. Let me just say, of course, what these classes that Watanabe discovered are there somewhere, so they have to be explained in this picture, and they basically lie in the middle of these bands, and so they're in the ranges of degrees that we've excluded. So let me show you the picture, which is a lot easier to understand than the formula. So this is a chart of the homotopy groups of B top 2n. Oh, I didn't emphasize that very much before on the previous slide. Let me do that. This is all about even-dimensional Euclidean spaces. Okay, I'll talk about odd-dimensional ones in a moment. So what it says, so this dotted line in the middle is the Igusa stable range. So below that line is what people knew classically. So firstly, it says that pattern continues like in about twice the range that it was known. And then there are these bands of degrees in sort of blue and orange under which we don't know if this pattern continues. And I've been a bit badly behaved, and I've still drawn some orange dots under the bands because I know some things I'm not telling you. But basically, under the bands, you're not supposed to know anything. And outside the bands, it's just the standard pattern of the Pontryagin class dots and the Euler class dots. That's the statement. So this is somehow, what's crucial about it is it's not just saying that something is true up to a range, it's saying something is true outside of certain thin bands, okay? And the bands are such that in any given column, the bands eventually accumulate, and so you've excluded all degrees above some degree, but it's a quite high degree where you've excluded everything. So that's the chart of so this is basically what we know about the homotopy groups of homeomorphisms of an even-dimensional Euclidean space at the moment. Using a different kind of techniques, Manuel Kranich and I try to do a similar thing for homeomorphisms of odd-dimensional Euclidean space, or equivalently compactly supported diffeomorphisms of odd-dimensional Euclidean space. The methods are different, and so the kind of result we prove is different. It doesn't have this band pattern. It's just a complete calculation in a certain range, but the range is about twice the old range. It's about 2.5 times the dimension instead of 1.3 times the dimension. And what it says is the following. It says, it all looks very similar, of course. The first two terms are exactly what Fowler and Xiang told us. It says those continue to be there in about twice the range of degrees. And then there's a new phenomenon that shows up. There's a one-dimensional vector space that shows up in degree 2d minus 2. And again, these classes all have meanings. The ones in 4i are these Pontryagin classes. The ones in D plus 1 mod 4 come from algebraic K-theory. And this new one had to be there because Watanabe, if you go through and look carefully at his formulas, has promised us that at least one class has to be in this degree. And we find exactly one class, and so it has to be Watanabe's. And it corresponds to this trivalent graph, which is the letter theta. This is the smallest class in the graph complex, it turns out, and it has to be around there. And from that point of view, the argument or the proof is that, not the proof, the statement is that there's no more invariance. There's no more homotopy classes of the space of homeomorphisms apart from the one that Watanabe promised us has to be there. In fact, we don't use his result. We just calculate what it is, and in retrospect, it has to be his class, but we don't use that as an input. So that's a pattern, and graphically that looks as follows. So the statement's a bit different. There's a hard cutoff in degrees above slope 2.5, but apart from that, it's sort of it says that the pattern that we know under the dotted line, so the classical pattern, continues a bit further, but then there's a new class, which is a triangle in the picture, which corresponds to this theta graph. I just want to point out that this, in some philosophical level, is similar to the easy charts for BOD, in a sense that there's some kind of phenomena of slope 0, so all the horizontal lines consisting of Pontryagin classes. There's some kind of phenomena of slope 1, which is all the blue stuff, which, okay, you can think about it as being many parallel lines of slope 1, consisting of blue stuff. But then there's some new phenomenon of slope 2, which is the triangle classes. And so what I want to explain is a proposal that would explain this kind of phenomenon. Like, why should the homotopy groups look like they're some kind of superposition of different phenomena happening on different sort of frequencies or scales or something like that. So this band picture, I want to emphasize, suggests that what's going on is some kind of superposition of many different phenomena corresponding to the different bands. Maybe there's some underlying phenomenon corresponding to just the Pontryagin classes. And the story probably looks complicated for any given disk because it is the sum of many sort of dissonant phenomena happening on different frequencies and so on. It probably looks quite complicated. But maybe if we look at the charts in this kind of way and we try to understand the phenomena one at a time, maybe they're not so complicated. So maybe we should think of the homotopy groups as being a superposition of phenomena happening on different scales or on different wavelengths or whatever you like. And what seems to happen is that the kinds of phenomena that show up depend on the parity of D. Right? The chart for D odd was quite different from the chart for D even. But among all the even ones, things just seem to scale with various slopes. And between all the odd ones, things just seem to scale with various slopes. So there's a mechanism in homotopy theory that is designed in some sense to explain this kind of thing. It's called orthogonal calculus. And it's a little bit esoteric, but I want to explain to you some things about it. It's a calculus of functors. So we're doing calculus not with functions on the real line or something, but with functors from one category to another. And the kind of functors that it involves is functors from the category of real inner product spaces to the category of topological spaces. And the one that we're going to be interested in is the functor that sends a vector space V to B of the group of homeomorphisms of that V. Okay? You can forget the B in front if you're not happy with that. It just sends V to the group of homeomorphisms of that vector space V. So this is a functor. If I have an embedding of one inner product space V into another one W, it has a canonical complement. And if I have a homeomorphism of V, I can get a homeomorphism of W by taking the identity in the complementary direction. And the game of orthogonal calculus is to think of things like this as though they were functions and to try to develop the notion of calculus in the sense of Taylor approximations. Right? Not calculus in the sense of differential and integral calculus, but calculus in the sense of polynomial approximation for functors instead of for functions. So let me try to say a little something about that. It's analogous to calculus and Taylor expansions of functions, but it's not meant to be more than an analogy. Okay. So the first thing I want to say what it means to be polynomial. If I'm going to talk about polynomial approximation, I better know what I mean by polynomial. So here's a definition of a polynomial. A function is polynomial of degree r if when I take its r plus first derivative, it's 0. That's the definition. So as long as I have defined what I mean by derivative, I can then define by the same sentence what I mean by being polynomial. So that's what I do. And I declare the derivative of a functor to be the following. It's like what you do with finite differences. I take the value of f at a vector space V. V canonically maps to V plus the real line. So f of V canonically maps to f of V plus the real line because f is a functor. And then I take the fiber. So I take the difference of those two things. That still depends on V. It's still a functor in its own right. And I declare this to be called the derivative of f. Okay? It measures the difference between the value of V and the value of V plus r. And if I can iterate this, so I can take many derivatives. So I can declare a functor to be polynomial of degree at most r if when I take its r plus first derivative in this sense, I get the constant functor that's a point always. So, of course, you can define whatever you like. Right? We're mathematicians. You can go and make a definition if you want to. Fine. It turns out that every functor has a best approximation by a functor that's polynomial of degree at most r. This is abstract, blah, blah. Like, you don't know what it is. It just has one. And not only that, but they assemble into a tower because the best approximation of degree 2 should be better than the best approximation of degree 1, and so it should map to it, and so on. So they assemble into a tower called the Taylor tower of the functor. And I'm going to reveal something on the slide now, which looks like a horrific equation. And do not be worried that you don't know what any of the symbols involved mean. It's just to be mathematically honest. So the main content of this theory is that the homogeneous polynomials, so the differences between the rth and r minus first approximation, have an extremely constrained form. I've written what the form is out of mathematical honesty, but you shouldn't worry. The main point is they have an extremely constrained form. I'll talk through it very briefly. What you get to do is they have to be a functor of the following form. You take your vector space, V, you tensor it with little r copies of the real numbers, and you one-point compactify that to get a sphere. That has an action of the symmetries of r to the r, which is the group OR. And so whenever you have anything else that has an action of OR, you can somehow tensor them together and divide out by the difference. And you do that. So whenever you have anything that has an action of OR, technically it's an OR spectrum, you think of that as being the coefficient of like the nth Taylor coefficient. You can form this thing, and that will be a homogeneous functor for sure. And the non-trivial theorem is that every homogeneous functor looks like that. And just looking at this formula, if you're interested in calculating in algebraic topology, you can check that this has exactly the behavior of a band of slope R. The homotopy groups of this rationally only depend on the parity of the dimension of V, but where they show up depends on the dimension of V in a way that scales with R. That's an easy calculation to do, I promise you. You don't have to do it yourself. So this is the point. The homogeneous functors are somehow classified, and they exhibit exactly this band kind of behavior. So it would be outrageous if the band behavior that we see for B top V was not explained by this kind of story. So let's see what happens. So the zeroth Taylor approximation, it just turns out means evaluate your functor on like an infinite dimensional inner product space, R to the infinity. So let me just call that B top. And we can calculate that with the information I've given you. That just corresponds to taking, that just corresponds to taking the horizontal limits, and we just see that these orange dots that I had on all the charts. It's one class in every 4 degrees. The first derivative is more difficult, and it's essentially a theorem of Waldhausen that it is the algebraic K-theory of the sphere spectrum. Again, it's not important what that is for the talk. What is important is that it has nothing a priori to do with manifolds or anything like that. It has nothing a priori to do with homeomorphisms of Euclidean space. It is, in some sense, an algebraic object, except maybe in the modern sense of higher algebra, so algebra of spectra instead of sets. And this accounts for, I said maybe 2 or 3 times earlier in the talk, K-theory and related to something, and this is where it comes from. It comes from the first derivative of this functor. And the calculations that I showed you that were joint with Manuel Kranich calculate, if you go through them, what the second derivative is. It turns out, it's not so important what it is, it turns out it has a sort of more complicated formula. It maps from the circle to the -1 sphere, which is something that exists in stable homotopy theory. But when you see formulas with lots of symbols, that's better than when you see, if I tell you something's called K of X, it probably means that K is a quite complicated construction, right? But if I say it's f of G of W, they're saying, oh, you do lots of simple constructions, but you do them one after each other, okay? And this is kind of similar. It's more symbols, but that means it's a simpler object, because it's like a concatenation of many simple constructions. In particular, it's simple in the sense that it just has it has 2 rational homotopy groups. It's a very small kind of object. And that corresponds to the fact that the bands had finite width. They could have been wedges, but they were, in fact, bands. So this suggests that all the higher derivatives also only have finitely many homotopy groups. They're relatively small objects because they were bands of finite width. So that suggests that this should happen. And so how should we say what they are? So now we get to the part that I'm calling a proposal. This relationship via the work of Watanabe, inspired by the suggestion of Kontsevich to think about configuration space integrals, suggests that you should study homeomorphisms of Rn by studying how it acts on all the configuration spaces of Rn. Sorry, Rd, I'm calling it. So look at all spaces of configurations of finitely many points in Rd. If I have a homeomorphism, I can act on the points and they move around, so I get an action on the configuration space. But I get an action on any configuration space of any number of points. And we could try to approximate, or imagine approximating homeomorphisms of Rd by automorphisms of all configuration spaces of all cardinalities. But we probably want to remember that if I have 2 points coming near to each other, and I have a homeomorphism, then it moves them to 2 points that are near to each other. So in other words, and 2 points that are near to each other, if you're far away, looks like 1 point. So there should be some compatibility between the automorphism I get for 2 points and the automorphisms I get for 1 point. And more generally, when points collide with each other, there ought to be some coherences that say what I'm seeing when I have a configuration of n points, but 2 are very close together and the others are very far over there, should be similar to what I see for n minus 1 points, because these 2 that are close together, I can't really tell that they're 2 and not 1. So this is obviously, horrific to make precise, but one can make it precise. And a convenient way to encode this data of all configuration spaces and all ways points can collide is in the so-called little disks operad. It's an object called ED. Again, it has a simple name, which means it must be a complicated object. And homeomorphisms will act on this object, roughly by the way that I just described. They act on all configuration spaces, and they preserve what it means to collide, and so they act on this object. So you can try to use this as some kind of approximation to homeomorphisms. Automorphisms of this very complicated object. Of course, it seems like a weird thing to do, because Euclidean space we're quite comfortable with. We're studying automorphisms of Euclidean space, and I'm saying, don't do that. Make a horrific object and study automorphisms of that instead. Why is that better? It's better for the following reason. When we think about Euclidean spaces, we're thinking about literal automorphisms of it, right? Functions from it to itself, which are literally invertible and so on. When I say automorphisms of ED, I mean automorphisms in some homotopical way. I mean maps that have homotopy inverses, not literal inverses. And that, it turns out, always makes things bigger, but it also makes things more manageable. So even though this is automorphisms of a more complicated object, it's a softer kind of automorphisms, and so it makes it more accessible. It makes it so accessible, in fact, that we just know everything about it. As a very recent work of Frest, Turchin, and Willwacher, we have a complete description of the rational homotopy groups. Complete description means we have another thing called graph homology, and we have the promise that the homotopy groups of this are isomorphic to graph homology. And graph homology is a generalization of these vector spaces of trivalent graphs modulo IHX that I mentioned earlier, meaning that they're difficult to compute, but they are combinatorial and in principle computable on a computer if you had a very big computer. So here's an exercise you can do. You can imagine that you can make an orthogonal functor out of B of automorphisms of the little V disks for any vector space V. Instead of using the unit disk in RD, use the unit disk in our abstract vector space V. And you can think about what its derivatives would have to be and how well they approximate what we're trying to approximate. Okay, and this is how well you succeed. You calculate what the 0th derivative is of this, and you discover that you get 0. Okay, that doesn't feel like a great approximation to this space, but that's what you get. You try to calculate the first derivative, and you don't get 0. You get something that, if you're being generous, you can think of as being what's called negative cyclic homology. It's a copy of the rational numbers in every even negative degree. And there's another thing called negative cyclic homology, which is the rational numbers in every even degree. And you can say, I want to think of these as being instantiated by this identity. And that's not a bad idea, because it's well known that algebraic K-theory is related to negative cyclic homology. There's at least a map between them, as there should be, because this functor is meant to map to that one. But the higher ones, it turns out, you get exactly the following behavior. They're supported in finite bands of degree, and they're described in terms of graph homology. So the proposal, then, is as follows. It seems plausible to me that the higher derivatives are just the same. Higher meaning 2 and higher. And so that would suggest that it's like having two formal power series where only the 0th and first coefficients are different. All the higher coefficients are the same. And maybe we agree that they're meant to be something like analytic functions, so that they're given by their Taylor series. So that means if you want to get one from the other, you only have to fix them by using linear functions. And the way that's implemented in homotopy theory is that you can reconstruct, the proposal is you can reconstruct homeomorphisms of RD from automorphisms of this little D disks operad, as long as you fix their 0th and first derivatives to agree, which they don't agree, so you force them to agree. And after you do that, you recover the space of homeomorphisms of Euclidean space. This is the proposal. As evidence for it, another reformulation of what Kreinik and I proved is that on second derivatives, this is true. So they have the same second derivative, and the map is indeed an isomorphism between the second derivatives. And I think if this is true, then it gives a kind of, it's a kind of remarkable statement, because it's saying that many a priori very unrelated things are in fact related. So we have homeomorphisms of Euclidean space, which is the object under interest. We have algebraic K-theory showing up. We have, although I hid it a little, we have algebraic L-theory showing up for people who know what that is. And we also have all these graph cohomology groups showing up. And what this says basically is that you recover, at least at the level of homotopy groups, let's say, you recover the homotopy groups of the space of homeomorphisms of RD by taking the graph homology and taking algebraic K and L theory and gluing them together along this thing called cyclic homology. That's the proposal. So this is what we're trying to establish at the moment. Let me just finish by showing you what the consequence of this will be. So this is a chart of the actual homotopy groups. In principle, there's a question mark on the chart because this relies on the proposal. This is what the actual homotopy groups of the space of homeomorphisms of even dimensional Euclidean spaces will be. So it's up to the second blue line, it's things we've already discussed, and then all these lines of various slopes are this graph homology using the computer calculations done by Willwacher and his collaborators. And I've just put them on my picture. And as we see, there's different phenomena happening on different sort of scales or different wavelengths. And this is, at the level of homotopy groups at least, this is what the full answer is supposed to look like. Of course, this graph homology business is a little bit like the homotopy groups of spheres, and it's also a little bit like prime numbers, in the sense that probably you're never going to be able to give a closed formula for all of it. Probably. So somehow, I consider the work to be done once, or the topological work to be done, once we've explained that homeomorphisms of Euclidean space is explained in terms of graph homology, which is a completely algebraic object. Now it becomes an algebraic quest to say things about that. And Thomas Willwacher and his collaborators have many papers where they say things about that. But it's somehow now beyond the scope, I would say, of differential or geometric topology. So, of course, we still have to establish this proposal. This is not done yet. I'm very sort of confident, but we still have to do it. And thank you for your attention.